Hi, this is chapter 5, and in this chapter, we're going to extend the chemical formula topics that we learned back in chapter 4. In this particular chapter, we're going to take a look at the chemical formula, and from the chemical formula, we're going to figure out how the atoms are arranged, and then come up with the something something called the Lewis structure. The Lewis structure shows how the valence electrons tie these atoms together, and then through the Lewis structure we're going to be able to predict the shape of these chemicals. From the shape of these chemicals we will be able to tell whether or not these chemicals are more charge or less charge on one side of the chemical versus the other. This is called the polarity, and the polarity property of a chemical is important because it allows us to figure out whether that chemical will dissolve in water or is insoluble in water. It'll determine whether or not when we take a drug, for example, whether it can be um, washed away from our system or it's going to adhere to the fat in our bodies. So these are important concepts, and it applies especially in the medical field, where scientists are always trying to find a magic bullet to take care of our ailments, and it's the shape of the chemicals that determines whether the drug is going to be effective or not. So this chapter is about structural shapes and properties. The picture that you see right here is a picture of G.N. Lewis, and G.N. Lewis is the scientist that came up with something called the Lewis dot structure. So before we proceed, let me just review some concepts for you. Remember that matter can be classified as mixtures or pure substances. Pure substances can be classified as elements or compounds, and compounds can either be ionic or covalent. Ionic compounds are when electrons are transferred from one element to another, and so you have cations and anions involved in that particular substance. Covalent substances are when the electrons are shared between the elements that are tied together, and the electrons could be equally shared, in which case it's called a molecular covalent, or it could be unequally shared, in which case it's called a polar covalent. Polar covalents are when the bonds, or the force that ties two atoms together to form a bond, those electrons are drawn to one atom to a greater degree than the other. That's what we mean by polar covalent. Now, atoms and ions are most stable when they have a completely filled outer shell, and that's called the octet rule. They will either transfer electrons, accept electrons, or share electrons. And you saw this back in chapter 4. There are many exceptions to the rules, like transition metals can have more than 8 electrons. Sometimes atoms will not have the full 8, and they're perfectly stable with 6 or 4. But for the most part, what drives a chemical reaction, what drives these products to form, is the fact that they want to have the same number of electrons as a noble gas. So, bonding theory is the theory that explains why these things occur. It tells that the atomic orbitals of each element, when they form a compound, forms molecular orbitals, and the electrons that are found in each element rearrange themselves so that they tie the atoms together. This is called bonding theory. One theory in particular is valence bond theory. It tells you that the valence electrons, again valence means outermost electrons, are what is responsible for tying down the shape or tying down the atoms, and it dictates the shape of the chemical. Another theory is called molecular orbital theory, and it's the It's the orbital that forms when two atomic orbitals come together to form a bond. And through both of these theories, we can get a good idea of what the shape of the chemicals happens to be and some of the properties that result from the combination of atoms. You guys don't really have to know the details of this, just understand how atoms come together to form the Lewis structure and what shape results because of the Lewis structure. So, in the valence bond theory, which is the main theory that we're going to be investigating in this particular chapter, is that the electrons, when they are in an atom, they tend to find or take on a geometry that places them as far apart as possible, because the electrons are negatively charged, and so when two negative electrons come in the same space, they'll repel each other. If, however, you do put two electrons in the same space, they must have opposite spin. If another set of electrons come in that same space, then they are repelled as far as away from each other as possible. So, the rules of the valence bond theory is that the electrons take on opposite spin in the bonding orbital. Strength of the bond is dependent on the overlap of the bonding orbital. Molecular orbital forms is the result of atomic orbital coming together, or the hybridization of the atomic orbital. The number of hybrid orbital equals the number of atomic orbitals that do come together. And the type of hybrid results from the type of atomic orbital overlap. So all this is theoretical, but it gives you an idea how, it gives you an explanation of how bonds form. Here's an example of two hydrogen atoms coming together. Here we know that the electrons, the single electron on hydrogen is found in the 1s orbital. So when the two hydrogen atoms come together, that overlap of the 1s orbital between the two hydrogen atoms form this, what we call a sigma bond. And the two electrons are shared between the two hydrogen atoms. Here's another example of a hydrogen and a fluorine atom coming together to produce hydrogen fluoride. In this particular case, the 1s orbital on the hydrogen, and then that unpaired electron on the fluorine. Remember, fluorine has 7 valence electrons, but there is 1 electron in the p orbital that's unpaired. Well, if we think of that 1 electron that's unpaired in the p orbital as found in this type of electron cloud, then what happens when these two atoms overlap, they form this sigma p orbital right here. So this is the molecular orbital that forms from a hydrogen and a fluorine. Now when two fluorines come together, remember that fluorine electrons are going to found in the p orbital. They're valence electrons, the last electrons that's unpaired. So when the two unpaired electrons come together, it's the two p orbitals that come together, and this is the overlap that you get. So scientists have a good way of explaining how these atomic orbitals come together, the hybridization, or the change that results when these atomic orbital overlap. This is sort of beyond us, but again, it just shows you that we can figure out what type of shape these chemicals have, these compounds have, based on the atomic orbital overlap between the atoms that come together. Now let's go back to basics. What we are going to do is learn about Lewis dot structure. The Lewis dot structure for the atom is simple. It's just a dot representing the valence electrons of each atom. Remember that hydrogen has 1 valence electron, lithium has 1 valence electron. It is in the 1a family. Therefore, we represent the Lewis dot structure as the elemental symbol H and 1 dot, or the elemental symbol Li and 1 dot. If we want to do sodium, we do Na with 1 dot. Beryllium is in the 2a family. Look at the periodic table. It's got 2 valence electrons. So what we do is we represent the Lewis structure with the symbol Be and 2 dots. And we put the dots, the valence electrons, remember the dots represent the valence electrons, in opposite sides. Boron has 3 valence electrons, carbon has 4, nitrogen has 5. The way we draw the valence electrons is we generally draw it in 4 corners. Here, to the right of the element, to the back of the element, to the top, and to the bottom. These are the 4 corners where you are going to generally write the valence electrons. And then when you have to pair up the electrons, you're still putting it in these places, but now you put 2 electrons in these places. Remember that these electrons are going to have opposite spin. They're going to have opposite spin. So nitrogen has 5, oxygen has 6, fluorine has 7, and neon has 8. Neon's perfectly happy and doesn't react because it's got a full octet. Helium is the only noble gas that doesn't have 8. It's satisfied with 2. So these are the Lewis dot structure for the elements. Pretty straightforward. You just have to figure out how many valence electrons and you draw dots representing these valence electrons. Now, how many bonds or how many of its electrons will an atom share? And if it can share an electron, then it can form a bond. For every 2 electrons between an atom, that represent 1 bond. So if we take a look at the halogens and hydrogen as well, we find out that the halogens has 7 valence electron, 1 unpaired. Hydrogen also has 1 unpaired electron. So it's natural to believe that that 1 unpaired electron is going to be shared with another atom, and so its tendency is to form 1 bond. The chalcogen or the oxygen family has 6 valence electrons. 2 of them are unpaired. So oxygen prefers 2 bonds. It can have 3, but it prefers 2 bonds. Nitrogen has 5 valence electrons. 3 of them are unpaired. It prefers 3 bonds. Nitrogen can have 4, but it prefers 3 bonds. Carbon always has 4 bonds. Okay, carbon is one of those special atoms. Carbon is responsible for organic chemistry. It prefers almost always 4 bonds. The exception is carbon monoxide and carbon disulfide. Carbon monoxide looks like this, and carbon monoxide has 3 bonds, like that. The carbon has 6 electrons in the bonding right here, 2 more here, so that's 8 around that carbon atom. It obeys the octet rule. The oxygen, on the other hand, you can see that the oxygen has 6 right here that's shared in the carbon, 2 here, and so again that's 8. So in carbon monoxide, both atoms obey the octet. But in this particular example, carbon monoxide only, the carbon has 3 bonds. Let me next show you a series of examples of some compounds, how many total valence electrons each atom brings to the table, and then the bonding scheme for these chemicals. So here's HF. Hydrogen brings in 1, fluorine brings in 7, total of 8 valence electrons. This is how it would bond, okay? And the number of unpaired electrons is 6. 1, 2, 3, 4, 5, 6. 6 divided by 2 is 3. And so that's the number of lone pairs. And you can see these are lone pairs. Why are they called lone pairs? Because they're alone and they come in pairs. So that's the Lewis structure of HF. Let's take a look at another one. Let's consider a CH4. That's methane. Carbon comes in with 4, hydrogen comes in with 1 apiece, but there's 4 hydrogens. That's a total of 8. This is the bonding scheme. There are no unpaired left over after you use these 8 electrons in the bonds. Remember that each bond represents 2 electrons. You can draw a simple line to represent the 2 electrons in a bond. And so this is the Lewis structure right here. Let's look at NO. NO brings in 5 oxygen. Nitrogen brings in 5, oxygen brings in 6. But the plus tells you that this chemical right here has 1 less electron. So you have to subtract 5, subtract 1. If it was a negative, then you would need to add 1. Okay? You need to add 1 because if it was NO negative, it means that this particular structure has 1 extra electron. The fact that in our example it's NO plus, it has 1 less electron, it's got 10 total valence electron. The bond between them is 1 bond. That means that we subtract 2 for that 1 bond. There's a total of 8 remaining electrons that is left unbonded. That means that there are 4 lone pairs. So if we did this, we would do this. That's 2. That's 1, 2, 3, like that. So if you count, there's 2, 4, 6, 8, 10. The problem with this structure, okay, is that if you count, this nitrogen only has 6 valence electrons. This nitrogen only has 6. 2, 4, 6. It doesn't obey the octet rule. This oxygen only has 6 valence electrons as well. 2, 4, 6. So this structure, the way I drew it, is probably not the correct structure because it disobeys the octet rule. In this discussion, what you will learn is that there is a trick in drawing these Lewis structure, so you come up with a structure that satisfies the octet rule and satisfies the fact that there should be 10 dots or 10 electrons in this structure. This is the answer right here. If you count, this nitrogen has 2, 4, 6 electrons tied up in this triple bond and 2 more here. That's a total of 8. This oxygen has 2, 4, 6, 8 electrons around it, and there's a total of 10. 2, 4, 6 tied in the bond, 8, 10. So this right here would be the correct Lewis structure. But again, how did we come up with that? Well, I'm going to show you the trick on how to come up with the Lewis structure in the next few slides. Here's an example for formaldehyde. Sometimes we do ball and stick models and we color code the atoms. So this formaldehyde has a carbon in the center, an oxygen at one part of the triangle, and then hydrogens in the other 2 parts. So this is formaldehyde. And what you will find is that this is the structural arrangement, and then we can draw the way the electrons are arranged around these chemicals. This is difluoromethane. Again, carbon, carbon, and fluorine, fluorine. What you guys are going to learn in this particular section is how to put the valence electrons in the structure. Like that. So let's consider a simple example, classic example like carbon dioxide. In carbon dioxide, what you have is, we know that carbon dioxide is CO2. We also know, or if you don't know, I will remind you that the first element in the formula is generally a central atom. That's the center part of the atom in which all the other atoms are going to surround it. So in a formula that you have, the first atom in that formula is the central atom, except when that atom is either hydrogen or fluorine. That's because hydrogen and fluorine can never be central atom because they can only take 1 bond. But if it's any other atom other than hydrogen and fluorine, that'll be your central atom. The other atoms after that are your flanking atoms. And this is for simple molecules that only have 1 central atom. So in carbon dioxide we have a central atom, carbon, oxygen, and oxygen. We also know that carbon has 4 valence electrons, and oxygen has 6 valence electrons. So let me represent that with 6 dots. I'm going to put 2 right here, 3, 4, 3, 4, and then 2 right here. I already know how I want to write my Lewis structure. That's why I'm putting these electrons in this fashion. So what you can do is write the Lewis structure by inspection. Sometimes you can do it if it's simple enough. Remember that in the Lewis structure, you want to make sure that you strive for the octet rule. This oxygen right now has 6. 1, 2, 3, 4, 5, 6. The dots in blue. We can give it 8 by sharing these two between oxygen and carbon, and sharing these two right here between this particular oxygen and carbon. And when we do that, this oxygen now has 8. In this particular case, 2, 4, 6, 8. We can do the same thing on this side. We can share these 2 electrons between that carbon and that oxygen, and these 2 electrons right here. And when we do that, what we have is this oxygen has 2, 4, 6, 8. This carbon, by virtue of sharing 4 of its electrons with 4 other electrons, now has 8, and so this would be the Lewis structure. And you see that right here in this diagram. That's what we see. And this would be the Lewis structure. The Lewis structure shows carbon with 4 bonds, 2 to each oxygen, and then remember that carbon's bringing in 4, oxygen is bringing in 6 apiece. So for this structure we need a total of 16 dots, or combinations of dots and lines representing 2 electrons. So if we take a look at this right here, we have 2, 4, 6, 8, 10, 12, 14, 16. So in terms of total valence electrons, this structure satisfies it. In terms of the octet rule, this structure satisfies it. In terms of how many bonds carbon prefers, we see it prefers 4 bonds. 1, 2, 3, 4. It has 4 bonds. How many bonds oxygen prefer? Oxygen prefers 2 bonds apiece. This would be the correct Lewis structure, and we were able to do it by inspection. But sometimes it's difficult to do a Lewis structure by inspection. So what is a good, clever way of doing that? Well, this is what I call the bond table. Now I realize this particular slide is busy, but it just kind of sets the stage of how you would come up with the Lewis structure. The first part of this discussion tells you the atomic connection. The atomic connection tells you how the atoms are arranged in 3D space so that you can link one atom to the other. Keeping in mind that in a formula, the first element in the formula is generally the central atom, except when it's hydrogen and fluorine. Okay? Now the number of bonds. The number of bonds is determined by the valence electrons that each atom possess and obeying in trying to strive for the octet rule. So what you want to do is you want to take the electrons that each of the atoms is contributing to the structure. You want to arrange those valence electrons, and you want to make sure that the octet rule is obeyed. Now some electrons in that total valence electrons are going to be used for bonding. Some electrons will not. Those are the remaining electrons that is not used in bonding, and those will make up what we call the lone pair. So the way I like to go about this is by something called the bond table. And the bond table is simply that. What we do is we put the formula that we're going to be writing right here. We do a table that looks like this. And what we do is we have 2 columns. One called OE. OE stands for octet electron. The other one's called TVE, total valence electron. Next we break down the elements that are involved, we've got 1 carbon and 2 sulfurs. Now in the first column called OE, this means octet electron. This means octet electron. And it basically tells you that most elements want an octet, except for hydrogen, which is satisfied with 2. So here you either put 8 or 2. You put 2 when it's hydrogen, you put 8 for any other atom. So for carbon, we put 8. For sulfur, we put 2 times 8, which is 16. So for this column, if each of these elements were totally satisfied with an octet, we would have to worry about 24 electrons. Of course, we don't have 24 electrons. Carbon is coming in with only 4 valence electrons. Sulfur is coming in with 6. We don't have 24. But in a perfect world, in a perfect world, we would have 24 electrons to satisfy the octet rule. In reality, we have 4 for carbon. We have 2 times 6 for sulfur. That's a total of 16 valence electron. But guess what? If we take 24 and we subtract 16, from that difference, which happens to be what? 8, tells us the number of electrons we have to commit. To bonding. So if we think about 8, and we know that there are 2 electrons per bond, this structure has 4 bonds. Okay, this structure will have 4 bonds. That's what the bond table tells you. It gives you an idea of how many bonds the structure has. Now, we've used 8 from this 16. Because remember, this value right here, the 16, is the total number of electrons we're going to have in this structure, but we've just used 8 in bonding for a total of 4 bonds right here. 4 bonds result comes from 8 electrons. So if we take 8 away from 16, we have 8 electrons remaining. So the 8 remaining electrons is going to make up the lone pairs. So 8 divided by 2, we've got 4 lone pairs. So what does the Lewis structure look like for this particular chemical? Well, we know carbon is the central, sulfur is the flanking atoms. We know there are 4 bonds, so we just do 1, 2, 3, 4. It doesn't matter where you put it or where you start. There's my 4 bonds, those are my 8 electrons. We know we have 8 remaining electrons, and we need to satisfy the octet rule. This sulfur has 2 electrons here, 2 electrons here, so it already has 4. It needs 4 more. That's a total of 8 right there. It obeys the octet rule. Of this 4 lone pair, we're down to 2. This sulfur needs 2 more lone pairs. That right there gives it 8. And guess what? We've used up all our lone pairs. This would be the Lewis structure for carbon disulfide. And that's what you see right here. CS2, 1 carbon, 2 sulfur. This is a neutral chemical, so we put a charge of 0. Octet electron, 8 and 16, that's 24. Total valence electrons, that's 4 and 12, that's 16. The difference is going to be the number of electrons involved in bonding. If you divide that by 2, you get 4 bonds. That's what you see right there. If you take the total valence electrons right here and you subtract the 4 bonds, which represent 8 electrons from that, you get 8 electrons remaining. So what you have is this as your Lewis structure, just like I showed you in the example. So this is a clever way of coming up with the Lewis structure through a bond table. Let's take a look at another example. This is selenium dioxide. We write the formula there. We break it down to 1 selenium, 2 oxygen. First column is octet. Selenium has 8, oxygen has 2 times 8, a total of 24. But reality is selenium has not 8 but 6 valence electrons. Oxygen doesn't have 8 but 6 times 2 valence electrons, total of 18. If I were to ask you right now, how many bonds does this structure have? You would easily figure it out. You would say that 24 minus 18 is 6. 6 divided by 2 is 3. This chemical has 3 bonds. So how do we draw 3 bonds? Well, the atoms that are going to be tied together are the oxygen, the selenium, and oxygen. Put 1 bond between 1 oxygen and 1 selenium, a second bond there. Where you put the third one doesn't matter. You can put it there, or you can put it here. Doesn't matter. But you need to lay down 3 bonds. Now if we subtract 6 from this, we see that we have 12. That means that 12 divided by 2, we have 3 lone pairs. 6 lone pairs. So that's what you see right here. 12 divided by 2, 6 lone pairs. Again, you draw the lone pairs so that each atom satisfies the octet rule. You put 6 more on this oxygen. That'll give it 8. You take care of the flanking atoms first. Don't worry about selenium yet. Worry about this oxygen. It needs 4. Remember, we have 6 lone pairs. We've used 5 right now. The last 2 goes on selenium. If you count, this oxygen has 8. This oxygen has 8. And this selenium has 8. It obeys the octet rule. Here's another example. In this particular example, we have dihydrogen phosphate, but it's a dihydrogen phosphate ion, so it has a negative charge. How do we account for the negative charge? Again, we draw our bond table, H2PO4 negative. We have 2 columns. We break it down to, by the way, that's the structural arrangement. You wouldn't know that. I would have to give it to you. But when you do the bond table, usually the question is how many bonds? How many bonds on the central atom? How many lone pairs? You don't need the structure to answer those questions. All you need is the information from the bond table. Because the bond table, without even knowing how the atoms are arranged, tells you how many bonds. The bond table will tell you how many remaining electrons, which will tell you the number of lone pairs. So even if you don't know how the atoms are arranged, if you know how to do the bond table, you can answer a majority of the questions that are going to be coming up on your next quiz. So let's take a look at completing this particular Lewis structure. We have 1 phosphorus, we have 4 oxygen, remember it's PO4, we have 2 hydrogens and 1 negative charge. So phosphorus prefers 8, oxygen prefers 8 times 4, that's 32. Hydrogen prefers 2. You got to remember that. Don't forget, hydrogen is totally satisfied with 2 valence electron because it wants the same number of electrons as helium, which can only have 2. That's the exception. So, if this were a perfect world, we would have a total of 44 electrons, so that each of these atoms will have the same number of electrons as the noble gas. In reality, we don't have 44 electrons. Phosphorus has 5. Oxygen has 6 apiece for a total of 24. Hydrogen has 1 apiece for a total of 2. And then the charge, this negative charge right here, tells you there is 1 extra electron in this structure. So when you add this all up, what you have here is 32 electrons. So how many bonds in this structure? 44 minus 32 happens to be 8. 44 minus 32 happens to be 12. 12 divided by 2, 6 bonds. How many lone pairs? Well, if we subtract 12 from 32, we come up with 20. 20 divided by 2, this structure has 10 lone pairs. Even without doing the Lewis structure, I've already answered a majority of the question for Lewis structure. Let's see how it all plays out. we have the 6 bonds by connecting all the atoms. Remember, phosphorus is central. Hydrogens are connected to the oxygens. You won't know that, and so I would have to tell you. You notice there are more than one central atom. Phosphorus is a central atom, oxygen, and oxygen central atoms. Central atoms are atoms that has 2 or more bonds. So in this structure we have 3 central atoms. But we do have 6 bonds. 1, 2, 3, 4, 5, 6. And we do have 10 lone pairs. You probably need 6 on this oxygen. Okay, that's 3 lone pairs. You need 6 on this oxygen. That's an additional 3, so we've used up 6 already, lone pairs, for a total of, in this particular case, we've used a total of 12 electrons in our 6 lone pairs. This oxygen needs 2 lone pairs, so that's basically we've used up 6, and now we're down to 2 because we have 2 lone pairs, and this is where the 2 lone pairs belong. If you count, you're going to see that this oxygen has 8, 2, 4, 6, 8. 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 This phosphorus has 8 through its 4 bonds, and hydrogen's totally happy with 2. That would be the correct Lewis structure. The way we would write this is we would basically write the bonds, fill the lone pairs. We put a bracket around this structure to show that this is an ion, and we put a negative outside that bracket to show that it has 1 extra electron in its Lewis structure. Here are other examples. Exception to the octet rule. You know you have an exception to the octet rule, that is, the atoms won't have 8 around it, when you have an odd number of atoms. If you have NO and it's not charged, it's not negative or it's not positive, but it's neutral, nitrogen comes in with 5, oxygen comes in with 6, you're going to have an odd number. It's going to violate the octet rule. It's going to look like this. It's a correct structure, it just doesn't obey the octet rule. There are exceptions to the octet rule, a lot of exceptions. Sometimes, like in boron and beryllium, they're satisfied with 6 or 4 electrons, it's going to violate the octet rule. When you have elements in the 3rd period or lower, it's going to use its d orbital, it's going to have more than 8 electrons. So these are just examples of chemicals that violate the octet rule. So in summary, when you draw the Lewis structure, remember that compounds are formed when the electrons are shared or transferred between them so that they have the same number of electrons as, say, a noble gas. The way you determine the Lewis structure is you write the chemical formula, you figure out the atomic sequence. Remember that hydrogen and fluorine can never be central, so they're always terminal, they're always at the end. You lay down the arrangement of the atoms, and then you do the bond table. You write out the bond table. You have 2 columns, OE and TVE. OE is octet electron. In that column you can only put 8 or 2. Please remember that. That's a common mistake. TVE is total valence electron. That's how many electrons each atom is bringing to the table. When you take the difference and divide by 2, that's the number of bonds this chemical has. If you take the total valence electron and you subtract this quantity right here, the number of electrons you're going to commit to bonding, that'll be the remaining electrons. And if you divide those remaining electrons by 2, you get the lone pair. It's just a matter of piecing it together and making sure that when you piece it together that you go to the octet rule, that each atom wants 8 electrons in its valence shell. Hydrogen satisfied with 2. There are some exceptions, so you have to keep that in mind. So that is discussion on how to draw the Lewis structure.